It's fine? Okay. All right. Let's see. Is the mic coming through any speakers or no? I can't really tell. But, okay, that's fine. Well, it is what it is. So the subject for the day is modeling the BJT, the bipolar transistor. So this all is something that hopefully you've seen in 105, but we're just going to go through it really fast to make sure that everyone's up to speed on it. So sort of like the standard model that we just used to look at it is something like this right here, where we basically just have a couple of diodes here back to back. Sorry, I can't talk. Sorry, and one thing that you'll notice here is that this is doped more heavily. It's N. Sorry, I'm stuttering. It's N plus in the emitter, and the purpose of that basically is that you will that you want a high ratio of carriers injected from the emitter versus the carriers injected from the base. And so this is sort of like the standard model that we'll start from, and then we'll vary this and expand on it as we go. And then if you are to represent this as a circuit, then you end up with something like what's shown to the right. This is exactly the same thing. It's just drawn the way that you'll see it in a diagram, of course. And the same thing over here for the PNP. It's exactly the same. It's just the doping is inverted. And we actually flip it now. So at this point now, we usually have a higher voltage up here on the emitter. So I can hardly see my cursor here. So this now has a higher potential. So just to sort of give you an idea of what well, actually, no, I'll come down here and explain this first. So the way that we usually want to operate things is in forward active mode. And this is where we're getting most of the gain. So the other regions have their functions for the most part, but for the vast majority of everything that you'll ever do, this is the mode you want to operate in. It's kind of confusing because there's this mode over here called saturation, which if we were working with MOSFETs, then saturation would be a great thing. Because that's basically the operating region of a MOSFET is saturation, but it turns out that there's no relation whatsoever. It's just that whoever was making up the names wasn't making life very easy on anybody else. And so the way basically that we operate in this region is that the junction right here is forward biased, and this junction is reverse biased. If you think about it, if these are both forward biased, and saturation, then you basically have a straight current path all the way. Where's my cursor? There we go. You basically have a straight current path all the way through here, in which case you don't get any control from the base, which is not really what you want if you're going for a high gain. All right. So to sort of give you an idea of what a standard setup might look like, what some expected voltage values might be, I'll see if I can draw here. Sorry, this drawing is going to be a little bit sketchy, but all right. So here we have a simple BJT with resistive load. Here's our output up here that I just drew, and the input is over at the base. So if this is what's that? On the Blackboard? Yeah, I can do it on the Blackboard. It's just not going to be webcast, but I guess that's fine. So I'll just use the Blackboard for now. All right, so if we have our bipolar up here, let's say that we have a VCC of 3 volts up here, and that this is grounded, then normally, because basically we want this diode to be forward biased here between the base and the emitter. we'll have this voltage be around like 0.6 to 0.7 volts, somewhere in there, just depending on the characteristics of the device. And then this node actually, because the important thing isn't necessarily that this diode is explicitly reverse biased, but the important thing is that it's just not forward biased. And so as long as the voltage across here isn't enough to actually forward bias this diode, turn it on, then we're generally OK, which means that this node might actually be able to swing down to something like 0.2 volts. Or it could go up to 3 volts, the supply, except for the fact that at the point you do that, there's no current flowing. So usually, as we're choosing this resistor value, we'll want to set this node right in the middle at around 1.6 volts. So that's, the purpose of this isn't necessarily to explain the circuit per se, but it's just to give you an idea of the range of voltages that we're usually working with on something like this. All right. See, and then the two modes that we haven't talked about at all, one is cutoff. And basically, it's not very interesting. It just means that since basically both of the diodes up here are off, then there isn't any major current flowing, devices off, nothing happens, boring. And the other mode is reverse active. So basically, it's just flipped from forward active, of course. And what's happening there is that you would think that if you flip the device, you get basically the same behavior, just in the other direction. But actually, because of the doping, so here we see that the emitter is heavily doped and the collector is lightly doped, what you get is actually a device that has very, very low gain. So you can sort of flip MOSFETs, but with a BJT, you really can't because your gain just becomes horrible. And so while there are occasionally uses for a cutoff or devices that are close to cutoff or saturation, and there's certainly uses for forward active, I haven't really seen anyone try to use reverse active. It's just not just not common, just not useful. All right, so as you're thinking about all these modes of operation and how diodes are biased and so on and so forth, one way you can visualize it is as basically on axes like this, where on the x-axis you have the voltage between the base and the emitter. So it's basically the voltage across this diode. And on the y-axis up here, you have the voltage over this junction, the base and collector. And this just basically says that it says exactly the same thing. It's just graphical, basically. So usually, again, we want to be operating down somewhere in this quadrant, right? All right. So now we sort of have that, and we have like a basic understanding of the different modes of operation. We can sort of go on to talking about what actually is happening in these various modes. So I'll start going through that. Just a second. Let me get my notes out here. All right. So the first is cutoff again, and as we said before, that's not it's not all that interesting because basically these diodes are off. We say that really no current flows. So the base current is 0, the collector current is 0, the emitter current is 0. So not much there. That's kind of the end of the story. But the more interesting mode, like we were saying, is forward active. So here it actually gets a little more complicated. So this will be most of the math for the lecture. So if you can stay with me through this, then you're doing well. And then it will get easier after this, I promise. So one thing I'll basically just say as we're starting is that for all the calculations and derivations that we're doing throughout most of this lecture, and for that matter, that you'll find in the textbook as well, we'll assume NPN. It's about the same for PNP, of course, just all your signs are flipped. It a reasonable general rule that if you have like some intuition of what the sign should be, if your answer for like for some value comes out negative and you think it should be positive, then you can probably just flip the sign, because they really are exactly the same, just with the signs flipped. So if you do have the intuition, you can do it. All right. So first we have these two figures here, and I won't explain all of what these are right now, but we'll sort of go back and forth between these and the following on the equations that follow. So right now, this first figure up here is basically just showing the flow of the carriers in the device. So here we have electrons. I believe these are electrons because they're canceling with these holes right here. And then we have these holes that are flowing off in this direction. They're diffusing over that gradient. So that's kind of the basic figure we'll start with. Just keep in your head temporarily. We'll come back to it. And then this second figure basically is showing the concentration of the minority carriers. So basically in the base region, which is p-doped, the minority carriers are the electrons, which is actually what this says here. So this first N basically tells you that those are the types of carriers we're talking about. So in this case, the N carriers are electrons. Then the subscripts says whatever. Anyway, it's doing weird things here. So the first subscript is a P right here. And what that means is that just we're looking in the P region. So we're looking at the N carriers in the P region, and the second subscript here is a B, which just means it's the base. So that's just an extra sort of assurance, basically, that we're talking about what we want. And so the portion of this that we'll focus on for most of this is what's actually happening in the base, since that's kind of going to be the most interesting. So what we see is basically a charge profile here that says next to the junction basically says that next to the junction by the emitter we have a high concentration of these carriers, and then on the opposite side at the collector we have almost zero concentration, and that will come out in the equations. So there are three sort of things we're going to look at, and these actually correspond to the figure up above. Let me see if I can align these. Okay. All right, so the first thing we're going to look at is the electrons. They're injected from the emitter into the base. And so that's actually this right here. So this is the emitter, this is the base. So we're looking at this huge flow of electrons. All right, the second thing we'll look at is the holes injected from the base back into the emitter. That's this one right here. All right, and the third that we'll look at is the recombination. And that's what's happening here, where we have these two arrows that are running into each other and seem to be canceling out. It's basically that you have holes and electrons flowing in the same area, so they'll just cancel out. So I'll come back to this part a little bit later. So let's go into the math a little bit. So the first thing we can sort of look at, and this is actually a little bit backwards from the way that the equations are derived in the textbook. So in the textbook, Grawemeyer actually starts at this end from the basic physics and works up to an expression over here for the current. But here we're sort of working the opposite direction and breaking it down. So I may go in one direction or the other, just depending on what seems more clear at that point. But basically, the way that we can start to break this down is we have the base current right here, and we can split that up into basically the current density and the cross-sectional area. Because if you just size your device differently, you have a larger device, you'll have a larger current. So we like to get that factor out before we start. The next thing here is that we'll express this term here, the diffusion current density, as the can't talk as the well, I can't talk, but hopefully you all know what Q is. It's the charge of an electron. And here we have a diffusion constant, which at this point we're not going to talk about where that constant actually comes from, but I mean you can just be assured that it's a constant. So it's this number that basically has been characterized by the device physicists. And then this last term here is really what becomes interesting, which is that we're looking at the change in carrier concentration over this distance up here. So this is where we start to come back to this figure. And so we actually calculate this out and expand it. And what we get basically is that it's the concentration at this end, its concentration over here minus the concentration at this point, which is significantly higher, divided by the width of the base. And so what this comes out to is you can notice here that there doesn't seem to be much carrier concentration. So that's approximately 0. And so it's this other factor that's going to end up dominating, and that's what comes out over here in the math. So we can basically expand this whole thing to this form, and then this over here is the part that we now kind of ignore and just, or I shouldn't say we ignore it, but we express it in the future just as IS. Right? So that's, and so this is the form that we're usually looking at for this equation. So this is the first major component. And so we see up here, actually, if we go back to these sort of number conventions up here, is that this contribution, so remember we're talking about the flow through here, is actually what makes up the collector current, I sub c, which is going to be one of the two currents that we end up being most interested in. The other one that we're really interested in is the base current, and that's actually a sum of the other two components that we'll go into now. So these follow fairly similarly. So here it's the same thing. So we have so here we have basically the whole current into the emitter. So that's what we're talking about from this one up here. And it's expressed in the same ways. So we have the cross-section. Here we have current density. We expand that out, and we have the same derivative. Basically, we're looking at the concentration differences. And it comes out into a very similar form over on this side. So this is something that you can sort of just take for granted, because pretty much the math is laid out here. There's one note here in the notes that I actually want to highlight, since it's I think actually more important or more likely to cause confusion in the future. And that is basically it says that you can also replace this factor here. So this is the width of the region here. So it's WE. It says you can also replace this with L sub P, which is the diffusion length. So how far these holes actually diffuse. I kind of suspect that that's something that was added to the notes after the fact, because it's not that you could replace it, you really should replace it. That's kind of the right way to express it. Because if the holes aren't all diffusing, or I should say if they aren't diffusing all the way across the emitter, then you need to factor that in to the equations. So that's just one thing I'll mention there. And then it's also expressed in the textbook as LP. So that'll help you to follow along when you actually read. So that is that. So now we can go on basically to the third contribution. And so this one gets a little bit more interesting because it's actually different. And this, we said, is the recombination of holes and electrons in the base. So as we inject current basically into the base, let's see. So we inject current into the base here. We have to cancel that with electrons that are coming. We have to cancel that. We have to cancel that with electrons coming from the emitter, and so what we end up looking at here is basically the amount of charge. Now it's actually contained in the base, and then basically the lifetime of those carriers. So if we expand this out, this expression for QE, then what we get is 1/2, blah 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 blah. Turns out this expression right here, these first terms up to the WB, is exactly just the area under this triangle. So you multiply WB, this NP at 0, and 1/2 factor because it's triangle. Pretty simple. So you just integrate under that, and then of course unit charge and scaling it by the cross-sectional areas before. And we end up with this final expression that is shown right here, labeled as number 3, which expresses, again, the current flow basically through here. So, or I guess it's exactly the same as this current. So it contributes basically to the total base current, which we see here. So the base current is these last two factors that we talked about. It's both the holes flowing here from the base, and then the electrons basically flow in the opposite direction right here. So those two sum, and you get the base current. All right, so that's that at this point is sort of the worst of the math. So from here, we can start using a little bit more intuition to sort of figure out what's going on. And as we move out of this mode where we're mostly just looking at physics and equations, we actually can build up more and more intuition. And that eventually is where we want to head, because if we have to start from the basic physics for every single problem we're trying to solve, then we just become a human version of SPICE, which is why we have programs like SPICE, so we don't have to do that. All right, so the most important factor that we're looking at most of the time on BJTs is the forward current gain. And sometimes we'll see this as beta F. Sometimes it's just beta. It's the same thing. In SPICE, I think it's just capital B, capital F. So this basically is a ratio of the collector current to the base current. And so that, from the equations we had before, is equation 1 divided by equation 3 plus equation 2. And this basically, it just comes out in this big nasty expression that we simplify down here to something that's a little bit easier to handle. But what it comes down to is, there's a large factor here from the base width up there, so that's actually squared. So that should tell you something first is that the base width actually has a large contribution in the gain. And we'll talk more about that as we get a little bit further in. And then everything over here is just diffusion constants and on fabrication constants. And then here we have our delays. So all these things basically are coming out of just the physical parameters. So that basically says that this basically says that, as far as we can tell now, this beta seems to be independent of bias. It seems to be just physical parameters, but we'll actually talk about why that's not exactly true later, because again, we'll come back to this base width. So going down here, we have three, I guess, key points for maximizing beta. So we want a small base width, because that basically means that, where is it? Okay, so here it is. So if we have a small base width, then basically we have less recombination in the base, and more importantly, a higher E field to push the carriers through the base, which means basically that we're going to have a higher current. So that's how that plays in. And it turns out that we actually can turns out that we can actually start to modulate the base width by changing these depletion regions here, which we can do by applying a bias. So we'll get more into that in a bit. But that's why we actually focus on the fact that we want the base width to be small. And this also is done in fabrication. You keep the base as small as possible so that you get higher gain out of your device. Next thing we'll notice here is that basically the dopant concentration in the emitter should be much higher than the dopant concentration in the base. And this actually is what I mentioned on the, I think the very first page basically up here when I said, okay, that this has a very high concentration of dopants and the base and collector are relatively lower. And you can see the reason for that basically out of this equation, the fact that you have this ratio here of the doping concentrations. So that contributes also to the high gain. And the last thing is that basically you want the lifetime of the carriers to be large. So basically you want less recombination of the holes in electrons, which is one more reason why a short base actually helps. It kind of feeds back into that. So that kind of explains where our gain expression comes from. And then there's actually a more complete expression that you come up with from more complicated device modeling. This isn't something that we're going to try to explain or really even understand in lecture necessarily. This is more just so you know that life actually gets more complicated with these expressions. But this is more along the lines of something that you might see in SPICE. So SPICE uses these more complicated models so that you don't have to solve them by hand. But this is kind of the one thing that I'll comment on here, the injection efficiency. This is something that came up before. Let's see if we can. So the injection efficiency, see, maybe I didn't mention that. Okay. Actually, yes, I did. Okay, yeah. So the thing basically with the injection efficiency, sorry, I'm scrolling all over the place here, is basically that it's the ratio of carriers that are coming from the emitter versus coming from the base. And so basically here we're looking at what's going on in the base. We'll call this X. Here it's the carriers from the emitter. We'll call that Y. This whole efficiency expression basically just comes out to Y over X. right? And so this is really the most important contribution. The factors here with recombination, there are actually three recombination factors, are important, but relatively less so. So that's basically one little bit of intuition that maybe you can get out of this, is that the most important thing is basically the ratio of characters from the emitter versus from the base. And that is in some sense what's also expressed in the just the simpler expression, IC over IB. It's basically we want the base current to be as small as possible, so we get higher gain. Okay, so now we start getting into more of the true sort of circuit stuff, where we start coming up with all these various parameters. Oh, actually, before that, there's one thing here. So we had this beta to express the current gain. There's also a factor alpha that expresses the current efficiency. And it's pretty much interchangeable with beta. If you have one, you have the other. It's just sometimes a shorthand in different expressions that is a little bit easier to write, but the vast majority of the time we'll be working with beta. But I guess one thing to keep in mind about these values, just for intuition's sake, is that the value for beta you want to be as large as possible. You want it to be infinity ideally. Realistically, it's more often around 1 or 200 for the current gain, and then alpha then is going to be roughly 1. It'll be slightly less than 1, but getting pretty close. All right, so now into more of the circuit stuff. What all of this lets us do is we get to then basically show these is we basically get to come up with these large signal circuit models for the BJTs. And so this one basically just shows that, okay, we have some base current here flowing in, and then here we have a current source, alpha IE. Well, if we go back up here, we said actually that alpha IE is just IC. And that just comes out from this these steps here that have to do with us just flipping around the beta expression. And this basically is an example of where it just becomes a shorthand. So this, whatever, I can't write. But this basically is just IC. And then this down here is just our diode that we said existed in the beginning. So that just has a characteristic that looks like a diode characteristic. So that's fairly straightforward as that goes. So this is the common base model. So that means that everything is referenced basically to the base. I guess more often we'll actually use the model over here, the common emitter, where everything's referenced to the emitter. And that's actually what I was drawing up here earlier on the board, which is basically like that. In this case, the reference is this ground node. This is the small signal ground in the circuit. On the common base case, the base actually becomes the small signal ground. So you just have to be aware of which model you're using when you sketch it out. But it comes out to something very similar. Again, we have this current over here that that's beta IB. Again, that's just IC. It's the same thing. It's just a collector current, and we have this diode. So it's just a different way of representing it depending on what your focus is, what your goal is. All right. So now that we've expressed all that, turns out usually we don't have to use models that are all this complicated. We can simplify the models to here just saying that we can. Okay, so this actually corresponds to this one here. So basically, we can say that this diode here is going to just look like a voltage drop of roughly 0.7 volts, 0.6 volts, whatever. It's basically what it takes just to turn that diode on. And looking at it from the standpoint of large signal, that's a good approximation. It's not going to vary much from there. If it's much lower, then you're going to have almost no current flow. Your diode is essentially off. If it's much larger than that, your device is going to explode. And I have seen that in lab. You might too over the course of the semester. Some people will pass way too much current through the device, and it'll get hot and pop. And then the model on the right is the same thing, just for PNP. And here it's actually shown explicitly that these two are identical, the beta F times IB and alpha IE. All right? So the sort of summary of this sort of subsection is that like these more complicated models that we have are usually a waste of time. And that's something that hopefully will become impressed over the course of the semester, which is that our goal basically is to simplify the models as much as possible so that we don't have to do as much hand calculation, and we can get to the point, like we talked about last lecture, where you can just look at the circuit and know what's happening because the models are so simple you can just solve everything in your head. That's ultimately where we're going. All right, so this is basically just explaining why we can represent this as a voltage source, but I'm going to assume that everyone's comfortable enough with diodes. We can go on past that. All right, so the next region of interest, or next region to be discussed at least, as I said before, it's not of great interest, is the reverse active region. Again, it's very similar to what's happening in forward active. You can basically go through the same equations, except the important difference now is that we have this alternate value for beta. It's beta reverse, now beta R. Drawing tools again. That is roughly equal to this other expression. So this basically is comparable to the doping expression that we had, where was it? Right here. It was just based off of the diffusion constants and the doping, and the widths of those doped regions. And what it comes out to, the important thing is basically that because the various regions are doped as they are, because basically here the base is doped fairly heavily relative to the collector, we don't end up getting much gain out of it in the reverse mode. So with that, I'm just going to go on since that region's not all that interesting. Basically, you just get horrible device performance out of it. All right? So now we can start talking about what's happening in the saturation regions. So this is the region where we basically said that the diodes were just forward biased. We have a current path straight through. And so we can basically just represent these diodes as being voltage sources. They're both on. So basically that's exactly what you see. There's not much more to it than that. It's that these diodes are on, and they're going to flow current appropriately. You do notice that there's a little bit of a difference in the voltage across these diodes, and that's because of the doping differences. All right, so in this case, basically the current in the circuit is going to be limited basically by a KCL, which just says that the current flowing out here of the emitter has to be equal to the current flowing into the base and into the collector. There's that, and then it also says the attached elements, which in general are going to be either resistors or other transistors that are operating in different regions and won't allow that much current to flow. So these expressions that we derived earlier with beta and alpha don't apply anymore in saturation. So that It's basically just one more way of saying that you aren't getting the gain you want when you're in saturation. So those were derived explicitly for the forward active region. All right, so when determining a DC operating point, so you should first you can first assume that you're in forward active because most often that's where you're operating, and you have to look, do you have high enough VBE? So basically, is the voltage here at the base actually high enough that the diode is forward biased? And if it's not, you're in cutoff. I guess it's possible also that you're in reverse active, but most likely you're in cutoff if that happens. But if it is high enough, that you go and look at VCE. And this actually, right now, is a little bit of a shift from what we've been talking about before. So before, we've been talking about the voltage between the base and the collector. At this point, we're shifting our I guess, frame of reference or to basically think about it in terms of VCE, since most of the time we're going to reference everything to basically what's happening at the emitter, just because that's our most common configuration. So it's not anything major. I mean, if you just use a KVL, it's exactly the same thing, but it's just referenced differently. So usually we actually have this expression here that's called VCE sat, and you need at least this value of VCEs, so this voltage here between the collector and the emitter, to make sure that you're in forward active. Otherwise, you're in saturation. And so that's actually what I sketched up here on the board earlier when I said that this voltage can usually go down to about 0.2 volts or so without it causing problems. And so this is sort of more of the justification. Hopefully that makes sense now based off of the models we've gone through so far. All right, so with that, now we get into IV characteristics and more of the real circuit stuff in a sense. So the first thing is that this basically is nonlinear. So it basically means that as it stands, this IV curve, so this is the collector current versus the base voltage, is not easy to use. It's not very useful as it is now because we like to work with everything we basically like to work with everything being completely linear. This makes the math easier, and we're engineers and we're lazy. So we like the simplest models we can get. So what we actually do is we look at this in the small signal region. So that's most of what you did in 105, was you looked at everything in terms of the small signal models. And so that's what it says here. It's kind of hard to read, but pretty much what this says here is that if we're looking at things in terms of analog circuits, then we use a small signal model. If the circuits are digital, then we'll use piecewise linear. And the piecewise linear model is basically just the one that says this diode is off until you reach the on voltage, then it's completely on, and you get a straight line up. So that's basically all that means. All right, so we'll get a little bit more into where the small signal model comes from in a minute. Again, this is mostly review, but the thing here that we should know is we're most interested in the collector current as a function of the base current and VCE. And so that's what we get here is, so these various steps up here are the base current, and VCE is what runs along this axis. And so those are how we're going to try and explain this. So this actually has a slope to it, which we'll explain a little bit more as we go further in. But basically, the way you can start to think about this for why VCE actually matters is that if we go back to the fact that we want like a narrow base, then if you increase VCE, then you have a higher bias basically on that diode, which means that your depletion region is going to expand. And as a result of that, you have a narrower base, which means that you have a higher field across that base and less recombination. And so you're going to get more current. And so that's why you see an increase here. This is the point that we sketch out all these curves. These become pretty much sorry, I can't talk. At some point, these basically have a constant slope up here. And if we extrapolate that back, we come up with the early voltage. This is sometimes confusing for people because it's not a real voltage. There is no voltage anywhere in the circuit that is out here at negative 50 or negative 100 or negative 1,000 volts. This is basically just an artifact of the fact that we can extrapolate these out. And the person who found this 60 years ago was named Early, so he happened to win. So going on from there, so we can look more at what's happening physically. And this is basically the part that I just explained with if we bias this, then the base shrinks. This slope steepens right here. And if you remember back to the early equations that we showed, we're looking basically at the slope basically of that. Let's see, it was like NPB at 0. So actually, we don't live in. Sorry, this is of x in this form still. So we're more or less just looking at the slope of the base there to express, I guess, the main factor for where the current is actually coming from. So basically, we have a larger bias, wider depletion region, narrower base, larger IE, most of which is coming from IC, the collector current, which is what we're interested in. Okay. So this basically just says that IC is related to the slope, and that's what comes out of these two lines that are a little bit hard to read here. So I won't dwell on that too much more. Let's see. So at this point, now that we have this model that actually includes the slope, we have to incorporate this other fitting factor, which comes out of the fact that up here these have a non-zero slope. So this didn't show up in our original equations. Where did it go? Here it is. So this didn't show up in our original equations, but it's basically just a fitting factor that we introduced to get the right profile, essentially. And this VA, this early voltage, is something that just a device property that comes out of the fabrication process. All right, so this basically just says that the collector current has a VCE dependence. That's that. Okay. All right, so now we'll go a little bit further into the small signal models for the BJTs. The first model that's shown here is a fairly general two-port model. These models are very powerful because they're so general. You can express almost anything with them, and you'll actually see them more later in the course, to the point we start talking about feedback, because you can basically express more with them. And so these are right now expressed in terms of these y parameters. So there's y11, y12, y21, y22, and it's basically just ratio of the current and voltage setting one of the other parameters equal to 0. So I won't spend too much time on this. Just sort of know that it exists, keep it in the back of your mind for later in the semester. And at some point, we will come back to it. The more interesting model that we work with most of the time, and you worked with in 105, is the hybrid pi model. And so this basically just says that we have the bias voltage here, and we have this this value r pi, and that we'll start to look at later in GM and on r naught. So the important thing to sort of keep in mind here is that this all is specified by the bias point. So it's a small signal in that it's useful for working with small signals, but all of this comes straight out of the bias point. And we'll get and that'll hopefully become more clear as we go through the derivations of all these parameters. All right, so I think about the most important parameter that we'll look at over the course of the entire semester probably is GM, since that is basically your gain factor. 105, you might have learned that the gain is GM times RO. Well, that's true if you're talking about voltage gain, but really the sort of basic mechanism of a transistor is you take an input voltage and you turn that into an output current, so you end up with a transconductance, and that is, I think, a little bit more fundamental of a gain parameter. So basically where this comes from is it's the slope of this diode curve. It's IC over VBE. And so if we go through this expression and we substitute in our expression for IC, and so this is the simplified expression that does not include the fitting parameter, then basically from this exponential we can pull out the VT, and what's left is basically just still the expression for IC, and we get the GM is just the ratio of the collector current to the thermal voltage. So again, it's entirely based on the DC operating point. That's something I'm kind of trying to pound in. One side note is that this VT, this thermal voltage, is not the same as the threshold voltage that shows up with MOSFETs. Unfortunately, sometimes because the word thermal starts with TH, people will write the thermal voltage as VTH. And sometimes because threshold starts with a T, they'll write the threshold voltage as T. The way that we're going to try to express things in this class is that when we're talking about the thermal voltage, it'll be VT for BJTs. When we're working with MOSFETs and talking about the threshold voltage, we'll try and use TH. But it's very likely that somewhere along the way, one of us is going to switch conventions or make a mistake or leave something out, in which case you just have to be aware that when you're working with a bipolar, the only one that we really care about is the thermal voltage. There is no notion of threshold voltage with a BJT. And with a MOSFET, for everything I think that we're doing in this class, what we're interested in is the threshold voltage. I mean, certainly the thermal voltage still exists because it's just a physical parameter, but it's not really of interest as much in MOSFETs. All right? So that's pretty much where that comes from. So then to pull out the R pi value, again, basically, it's the ratio of the voltage at the base to the current in the base. And so we go through the math. And so this time we can say that we express the base current as the collector current over beta, because that was basically from how we defined beta earlier. And so that then, at the point that we can say, okay, now we have this ratio here, this it's a ratio of the collector current to the base voltage. That's exactly what we had with the GM. So now that just becomes beta over GM. And this really is where I would have stopped with this derivation. because this is the form that you will almost always use for expressing R pi. How you come up with it is beta over GM. But the point basically of continuing here is to make it really obvious that, again, at the point you end up with just something that's a ratio of the thermal voltage to the base current. It's just dependent on the DC operating point. And so that's something that we said we first looked at the small signal model is it's all just dependent on the DC operating point. All right, so then the last one, R naught follows in a very similar way. You're basically looking at the inverse slope, in this case, of this IV curve. And here we actually have to factor in the early voltage, because if we don't factor this in, you can see sort of graphically that what's going to happen is that our slope is going to be 0, our output resistance is going to be infinite, and we can just leave it out of the model. But that's not the case. So we actually have to factor it in here. And so going through a little bit of math, this basically just says we're evaluating it at the operating point, and then the point that we have to actually do this derivative, this component goes away because there is no VCE term, and then this is all that remains. This basically multiplied by the IC term out there, and follow some math down. If you trust the math, then what we basically end up with is this R naught expression, which is basically this early voltage plus this VCE. So this is not drawn to scale. Because usually the early voltage extends much further out, and the VCE is relatively small. So we can say is that the sum of those is roughly just equal to this early voltage, because often, the early voltage is somewhere in the range of negative 50 to negative 1,000 volts, depending on the quality of the device, whereas VCE is certainly less than your supply, which at most, if you're working with like an audio amplifier, it might be 30 volts, but in most cases, it's more like 3 volts or 5 volts. All right, and thus we end up basically with a hybrid pi model that we introduced before. Here's a summary of all the parameters. So far in the lecture, we've gone through a lot of derivations. And I know that there's a lot of math so far, because we're going through basically all the 105 stuff from the first 4 weeks in about one lecture. But these are really what you should take out, if nothing else. These are something that you actually ought to memorize, because you'll just be using them so much that it makes life so much easier if you don't have to rederive them. If you do have to use them on a test and you forget the expressions, it turns out that you can sort of figure them out again just by thinking about the units, basically. And we know that the a GM is basically has to be a current over voltage, and you only have two currents that you ever work with. There's a base current and a collector current. And you know that you want the GM to be large, generally. So you can, sort of figure out by, it's a little bit of intuition that it probably has to be the collector current if you forget. And then generally the smallest voltage you have is a thermal voltage. So again, that just comes from the fact that GM ought to be large. And then the same thing with these resistors. Basically, it just comes out of the fact that you have a ratio of voltage and a current. This actually ought to be flipped, because right now it's expressed as a current over voltage. This is actually, it's flipped. Anyway, that's obvious from the previous expression. So a few last remarks. The GM is actually independent of the specifics of the device. it's largely independent of, well, yeah, I mean, it's not truly independent of the device, but for the most part, since you're looking at it in terms of the bias current and the thermal voltage, you can pretty much treat it as it is. I mean, certainly the collector current does come somewhat from the device model, but it's also something that you usually specify as a designer, which is why we say that it's kind of independent of the specifics of the device. Then one more thing to kind of note is that the small signal model is only valid if your signal at the base is actually small relative to the thermal voltage. So when we say small, we're talking about smaller than something that's usually around 26 millivolts. If you're working with something where you expect to have high gain because you're employing a small, or I should say, if you're working with something where you expect to have high gain, then you're probably working with a small signal anyway, because otherwise your signal is just going to clip at the output. So, all right. So now we're going to start making the models a little bit more complicated, and we're going to start introducing other factors. So the first of those is the equivalent resistance over here looking into the emitter. And this actually ends up following in the math in pretty much the same way as the base resistance, R pi. And so if you look at those side by side, I don't know if I can actually get them side by side here, but it turns out all you really do is you replace the base current you had before now with this with the current from the emitter. You follow it through, and your final expression, instead of being VT over IB, is VT over IE. So it comes out in the same way, exactly the same math. But what starts to get more interesting, and so this hopefully will start to resonate with the intuition you developed in 105, is that, well, if we express this a little bit differently, then we can basically take this intermediate expression here, where it's alpha over GM, and say that, well, if we have any kind of reasonable gain, then alpha is approximately 1. And so this resistance ends up looking like 1 over GM. And if you think back to 105, that's what happens. If you look up into the emitter, or if you're working with a MOSFET and you look up into the source, then the resistance you see effectively is 1 over GM. And so that's more or less where that comes from. One thing to keep in mind is that it's not explicitly shown in this model, but if you actually do the small signal calculations, it still comes out. It's still actually present, but effectively it's just lumped in with the other parameters in the circuit, or in the small signal model. Okay. If you want to explicitly show it, then you can basically use the T model, which is just a different representation of the same thing. And in this case, what you actually notice now is that you don't have an R pi. That's been left out. And since we said before that, well, they're pretty much, I should say, like, since the math pretty much follows in the same way, it's not too surprising that, on the formal model where you don't explicitly have an RE, but you do have an R pi, that the converse is going to be true down here for the T model. The reason this is called a T model, it's not super clear from this, but basically if you cut this out, then the rest of the structure is a T. But for our purposes, we'll leave in the RO for now. One last thing is that you can express this in a couple different ways. Again, this is just a collector current, whether it's GMVBE or alpha IE, exactly the same thing. So it just goes back to the fact that with BJTs, there are a lot of different ways of expressing things, but what's actually happening physically is pretty simple. So there's the 1 over GM that we talked about before. So at the point that we go down to PNP, I don't want to spend a lot of time on PNP because it's really just the inverse of NPN. You can flip most of your signs and have everything work out. I mean, the small signal hybrid pi model ends up looking like this. I mean, that's what this note actually says. It's the same thing. It's just upside down. So that's something that hopefully by now you're fairly comfortable with. If not, we can talk more about it in office hours. But I want to go on to actually talking about the parameters that start affecting the frequency response. Since frequency response is something we're going to spend a lot more time on this semester than you spent on it in 105. I mean, you kind of touched on it in 105. You learned some basic calculations, but frequency response is going to be, one of the dominant things that we look at through this course. So first thing we do is, at the point that we have to consider frequency response, we have to make the model more complicated. And these are probably parameters that you've seen before, but we have this C pi right here. We have a C mu between the base and collector. We have an R mu, and we have an RB, a base resistance. Right? So this resistor is usually fairly small, but at the point that you get into higher frequencies, that actually becomes important. And so that's why we actually have to include it in this model, even though relative to everything else, it seems like it shouldn't be that huge of a deal, but it shows up later. All right, so going back down here, this is the same thing essentially we were talking about before, but from a different perspective. So before we were talking about the base width, we said that basically if we change this bias, then it's going to change the width of the depletion region, which means that the base width would be changing. But in this case, also, if we think about the fact that the depletion region is depleted of carriers, so there's not current that is readily flowing through it, then it basically acts like a cap. And so the plates basically of that cap are the edges of the depletion region. So, I mean, as we modulate it, those values for C are going to change. And so that's what's basically coming out in this figure. So over here, this is basically our C mu that we're talking about, and then over here between the base and the emitter is our C pi. Right. So it's I guess the important thing sort of to take away from this is that if you think about it, at your DC bias point, you just have some constant value of C, your capacitor value, and most of the time, that value will be like right around the constant value because that bias point. Except when you add in a small signal input, then this starts to basically vary a little bit with that small signal input, which is where this comes into play and becomes a little bit more interesting. And so that is responsible for some of the effects that you talked about 105, and we'll look at more later in the course. But I don't want to get too far into it now before I go off on a tangent and start to lose people. All right, so that's basically the gist of that. The rest of it is just some formalisms, but all right. So right now, let's start talking about the way you'll actually calculate this when you have to find out what this value is in a homework assignment or something like that. So what you have, if you want C mu, then you have this value C mu naught, and then splice has some other names like CJC or the voltage across it basically is VJC. But this basically is at like the zero bias point, that value of C mu. And so that's basically what I was saying before, where at your bias point it has some value, but what we're interested in is basically when we apply a voltage across it, how is it going to change? And that's what's captured here, where we have this expression square root of 1 plus VCB over phi j. And where this actually comes from is something that's outside the scope of the class. It's more of a device physics thing, but this is kind of an equation that it will come back to. So the parameter that we're really interested in when we're working with it is VCB, since that's going to be basically the signal we're applying to it. And then this phi j is basically a function of it's a function of the can't say it function of the anyway, I can't say it, but hopefully you can read it because I'm stuttering right now. But anyway, yeah, the built-in potential there. Okay, and so what we can end up doing is actually we can express this built-in potential over here as KT over Q, which is just a thermal voltage, times the natural log of basically factors that here all have to do with doping. So there's a dopant concentration in the base, dopant concentration in the collector, and the intrinsic carrier concentration down here, which is which is generally a fairly constant value for a given temperature. So basically, in general, so here we said that this was a square root, but in general, there's actually a fitting factor over here, m, which might be 1/2, so it might be square root, it might be 1/3. It sort of depends on how the junction is actually fabricated. But it's basically just a fitting factor. It's something that if you're doing something in Splice, for example, for your project, that's a factor that will just be given to you. If it's not given to you, then you can just assume that it's 1/2 and just use the simplified model, or the first model, I should say, up here. It's not necessarily any simpler, but all right. So there is a more detailed derivation here. I'm not sure if I'm really gonna have time to go through all of it, but I actually want to hit more of the key points. So I'm going to skip the derivation and say that these notes will be posted online if you really want to go through how this is all derived. But going on to C pi, it's basically the same idea where, again, we're just modulating this, except now here we have a region of charge. And so that's going to add in a little bit of complication. And so basically, actually, may not have time to go through all of this, but it ends up taking a very similar form, which is that this cap that we're looking at here is a function of of its value basically at the zero bias point and the voltage that you apply across it, and again, some other parameter down here, which is just which is, let's see, where is that calculated? Okay, well, I mean, this is basically just an analog to what's up above. I'm looking at my notes now and thinking that in the last 5 minutes, I probably don't have time to really do justice to everything in this discussion of C pi. So I think I'll let you go, and we'll pick back up on Tuesday. So there, question? What's that? Where will we post it? It'll be posted on the course website, which hopefully will be up soon. I don't actually have control over the course website at the moment, but it will be up there. It'll be up there with the annotations that I added to it, everything I marked up. So let's see. I haven't actually checked today. It might be up, but if not, I'll send an email to Clark and see if he's going to post it soon.